Hi, SIwave is a power integrity and signal integrity tool. Today we will be talking about the PI solver inside SIwave. We need to perform power integrity if one die or chip on the board withdraws variable current. Drivers, power amplifiers, TIAs, and many chips withdraw constant current. But most ASIC chips, they withdraw variable current. That means the current contains a DC value and a spectrum of frequencies. Consequently, we need to understand the response of the power plays along this spectrum. You start working with SIwave by uploading a CAD file. Do not try to build your PCB using SIwave. Although you can, that is not, however, the right way to use it. You can upload the file using any of the forms shown in this table. Before you start using SIwave, it's highly recommended that you go through your schematic and you study it very well. It will save you lots of time. We have here a PCB board. It has many power planes, as you can see here. We can select them all and solve them all together. Nothing prevents us from doing that, but we will focus on only one of them. Notice that SIwave put all power planes in red. That's because it solves them, it treats them in a different way when it solves for power integrity. The next few minutes are for people who are new to PI analysis and PI tools. SIwave, like any other PI tool, it understands the language of nets. When it uploads any structure, it looks for nets and what we call single nets. So single nets, they are electrically connected structure without the use of any external component. Single nets cannot be disconnected. When you want to analyze a power plane, you need to identify its nets. It could have just one net. It could have many nets like the one you see here. And if there are many, these should be connected using resistor, inductors, or capacitors, or what we call passive components. And that will construct what we call a passive link. So these two nets plus this component, they construct a passive link. Now, if integrated or discrete components, the one you see in black here, exist along the path, then SIwave will treat the passive links separately. SIwave is a linear numerical tool that solves only passive links. This is important for you to understand because it changes the way you read the schematic. When you read the schematic, you look for all the passive links in the power planes. So document them and document all the nets of these passive links. After solving the model, if you have something like this that has two passive links, you can take the results and cascade the different passive links of a power plane using a circuit tool. Circuit tool is available also with SIwave. It comes for free with SIwave. So you can analyze a net, you can analyze a passive link, but you cannot analyze two passive links with an integrated component in the middle. You cannot do that. You have to treat this independently and this one independently. When you upload SIwave from an ECAD, SIwave of course uploads all kinds of information from your CAD file, all kinds of information, including the stack up and the layer and all the information that exists there, the material, the stack up, the thicknesses, all of this, plus the components, plus all the connections between the different structures. So what is missing to do to be able to solve a problem? The only thing missing is to assign ports. That's all. So what you do, you click this button, you get the introductory panel, you click on PI, that's the one you want a PI analysis. Now the good thing about SIwave that no matter, first it starts, when you want to do something, it starts by selecting the solver you want to use. And once you select the solver, immediately SIwave opens a dialog box. This is a dialog box. Try to think about it as if it is a form of some sort, where SIwave will fill it up with as much information as possible. Then expects you to review the thing that it did, the assumptions that it made, and fill up whatever is missing. So for our case here, for example, it presents for us, it will give us a list of all the nets that exist in the board, whether they are power planes or even RF lines or control lines or anything. It provides them all. It displays them all in this section. So now I want to select one power plane because I want to solve it. So I will select 1.2, for example. So what I need to do is to assign ports. So notice here what it did. So SIwave, the moment you select a net to solve, and of course if you have a power plane or a passive link that has more than one net, then you have to select all these nets. The moment you select these nets of one passive link, immediately SIwave populate this section with all the connections to the components, whether these are passive components or non-passive components. You can hide what we call the parallel components, the RLC, using this button, and you are left with the ones that are whether they are in series or integrated components. So for our case here, we have a couple of integrated components. We are interested in analyzing the connection between voltage regulator and the CPU. So we put a port at the CPU and a port at the voltage regulator. So something like this. So we're analyzing something like this. Great. Then what you do, you are done. Of course, you can do what you can do in SIwave is you can save your setup. Specifically, if you have so many power planes, so many passive links. So, for example, I did this. I have, for example, another passive link. I can select it. I can also select ports. And when you do the setup, you select them one by one. And if you do this one, it doesn't mean that this is still working. This is still activated. I can also display them all at once if I want, and then assign ports, but it's going to be very annoying. It's better to go through them one by one net at a time. So suppose you have so many of them, then you can save it to a file of some sort under FCF, and later on when you upload the same model, you can load the setup. So everything is uploaded, so you don't have to go through it again. This is very useful, but when you select only one, there's no need to save it. It's very simple. So now I do configuration. So configuration, simply I'm asking SIwave to assign ports and assign the necessary setup to start the problem. Validate, it goes through the nets, it checks them in a physical way, making sure that there's no violations in terms of nets joined or disjoints or all the stuff. And once you are done, then you go to simulate. Now you are ready to simulate. As simple as that. That's how easy it is to use SIwave. So I click simulate. And here I specify the frequency band I was telling you about before. So as I said, this frequency band is determined from the shape of your current. Like you look at your current shape, how does it change? And what is the spectrum contents of it? So you say then the spectrum constant is up to here. Then you try to solve beyond that just to see what's going on after that. So that's how we determine our bandwidth. What is the maximum bandwidth we want to solve for? You can select other solver options. You look at more setup in terms of accuracy. Do you want balance? Do you want fast? Do you want more accurate, which takes longer? You can specify processing, how many cores you want to use. There are other stuff that you can look at for the setup. So I'm not going to change anything. I'm going to keep everything the same. You can also export the touchstone file. For now, I'm not going to do that. I'm going to show it later on. Then you say launch. So if I do that, or they solve the problem, I get here to the results, I get this option. So if I click right click, now we are looking at the results. So the first result we got from doing SI analysis is the S parameters, which gave me, as you can see, we can see the return loss, we can see the insertion, we can see the crosstalk. You can select to see them all, display them all, or display one at a time, one group at a time. Like for this case, I selected to see only the return loss. Here I'm selecting to see the insertion. Now this one, if you have so many power planes, if you have so many of them, then you can look at the crosstalk. Now, what's the problem with the S parameters? So these S parameters, they are normalized to 0.1 ohm. Now, we don't know what's the impedance of our power planes, and consequently, we know that these results are not reliable. You cannot trust them because you have to normalize the port to the right impedance that matches your power plane. So how can we tell? If we cannot tell, then we cannot use, even especially if you are looking at crosstalk. If you're looking at the crosstalk and you have so many lines, how can you trust the results? You cannot. You have to make sure that your power planes, the return loss of your power planes is extremely good, like -40, -50 across the band of interest, to make sure that the crosstalk results are reliable. So what do we do in this case? Then we have other options that you can do in SIwave. That's the beauty of SIwave. It gives you so many options, which is renormalize. Instead of you using 0.1, you have to change it to another number. And unfortunately, you need to keep playing with it until you get very good return loss. Once you get the best possible return loss, then you can tell that, okay, now I can look at my crosstalk. Now the results of the crosstalk can be trusted. What else can we do with SIwave? We can also look, in addition to looking at the S parameters, we can also look at the Z parameters. Now, the Z matrix, this is simply the Z matrix extracted from the S parameter by removing the effect of the ports. So by looking at Z, we are simply looking at the impedance of the power plane itself. And we focus mainly on Z11 and Z22, which represent the real impedance of the power planes, which is what we are interested in, because that impedance is what's going to affect the drop in the voltage due to the change in the current. Now, the main mistake that many people do when they look at the Z parameter is they try to optimize this curve as is. Unfortunately, no, you cannot do that. That's not the proper way. You need to make sure that your power plane is matching your voltage regulator model. So how do we solve this problem? We simply go back to our circuit and we try to replace our voltage regulator with its equivalent circuit. So we go here. So that's another powerful thing in SIwave. You can add equivalent circuits to certain connections you have in your model. And I will go design tools and I will say add generate a circuit element on components. And here what I do is I select the component. Remember we said when we upload SIwave, it uploads all the discrete components. So I will upload this one, and for example, and this is the designator. So what is this? Is simply this is the name of the part, but you could have so many of them on your PCB. For each location, it will have a designated reference name. So for our case, we have only one component, and it's called VRM1. Now we go here, we select the positive voltage, we select here the negative voltage of this component, and we say the equivalent circuit of the voltage regulator is almost like an inductor plus a resistor. You say create, and you can enter the name, you can enter the part number, it can be anything. And For the inductor, we selected 4.7 E-10, which is 0.47 nanohenry and 8 milliohm. If I do that, I say, okay, it will create one, and I already did that. Now, to make sure that it did create that component on that connection, you go back to here, and from Edit Tools, you check on the circuit element parameters. That's where you have all the list of everything that you have. So if I go to the inductors, I see my component here. And it's very important that you do that because sometimes when people generate circuits, sometimes it attaches itself to the positive, but the negative is not connected. So something went wrong during the connection, and I noticed that many times. So it's good to go back to this and check and make sure that the connection to the ground exists there. Otherwise, you need to click on this component, delete it, and repeat the connection again to make sure that it's done in the proper way. So once you do that, then you have only one other step to do. Let me go back to the same list, circuit element parameters. So you have to select the ports. So now that we put a circuit on our virtual regulator component, we don't need this port anymore. So what you do, you click here and you deactivate it. And by deactivating, now officially you have only one port from the CPU looking into your power plane plus the equivalent circuit of the source, your VRM. And if you do that and you solve it, go through this same process of solving it, which is simply whether you click here and you click PI, or you can go directly to simulation where we have the list of all the solvers that exist in SIwave, and you select SYZ parameters. That's exactly the PI. That's exactly a PI solver. You click here and it's the same table, same bandwidth, and you can adjust your accuracy that you want, and you say launch. And I did that, and now if I go back and I look at my Z parameter, suddenly, you know, as you can see, the standard way Z parameter supposed to look like when you are doing PI. And now this one is the one I need to focus on and try to optimize. Now, if we go back to this drawing for looking or studying the Z11, looking from the CPU, you notice here that we have a Z max, and this Z max is determined by how much voltage we are allowed to rail to drop. So delta V over delta I should be equal to Z max. And that's how we derive Z max. So Z max, practically there's a formula for Z max, and that formula, it's written here. It's delta V. It's the allowable voltage drop that we allowed for our die, divided over 0.5 times I max. So if I go back to I max, so I max it's this guy. What is the maximum current required by the die? So you need to keep your Z below that value. And that's where you start adding decoupling caps until you suppress it way below this value. Okay, what else can we do with SIwave? We can also do sensitivity analysis. And what this sensitivity analysis allows us to do is to see how sensitive our parameters, whether S parameters or Z parameters, to the change in the impedance of the components. So if I want to do that, you have to go to Home first and you select circuit element parameters, which gives you the list of all these capacitors, inductance, and resistor. You look for the ones that have in your power plane. So in my case, I have C11 and C12. They are used in this power plane. And you come to this column and you just click on it and it will turn into green yes, green sign yes, okay? Or you click on it again and it will be turned into no, cross. So that's how you activate the sensitivity of this. Like you want SIwave to calculate the sensitivity of the S parameters or the Z parameters with respect to these numbers. Then when you go and you do solving, when you try to solve the problem, again, we go back to the simulation and we select SYZ, or as I said before, you can go to this table and you select PI, it doesn't matter. This is to start from the beginning. If I go to SYZ, it means it will use the last one that I solved. That's the difference between the two. And if you notice, there's a sensitivity tab here. And all what you need to do is to activate them. You say, yes, I want to calculate S and Y and Z of this power plane, the sensitivity of these parameters to the two components I activated in the previous table. And you launch. And if you do that, this is what you're going to get. You're going to get a plot. And this plot is, for example, for Z parameters, is with respect to C11 and C12. So what you're looking at is the slope. We're talking about teeny weeny change. So the slope just gives you an idea how sensitive your Z parameters to C11 and C12. So you can turn off one of them. You can just look at one of them, and or you can both of them. You can look at it. Of course, you're going to have so many power planes and so many components, and you can of course study them one by one, and that's how you can tell if your parameters, Z parameters, is sensitive or not to these components. And if it's too sensitive, then you need to be careful, because remember, these are discrete components, and if they are discrete components, they don't have exact values. There's a delta in them, so you need to study how much is the delta, and let's hope that delta is small. So you can use the slope with the delta to be able to tell how much the Z will change here. And good thing here is the SIwave shows you the slope, the sensitivity slope with respect to frequency up to 1 gigahertz. So that's something very powerful existing in SIwave, and I noticed lots of people don't use it. So please make use of it. It will tell you a lot about your power plane behavior. What else can we do with SIwave? We can calculate the equivalent circuit of our power plane. Practically can compute the equivalent RLGC subcircuit. You can do that only for the case where you have no equivalent circuit of the VRM attached to your circuit. Practically, you have 2 ports on your power plane. So you click on right click, then select compute RLGC subcircuit. Try to select something very low frequency. Don't try to select something very high because of the complication at high frequencies. Then you have to assign sink and source. If you do automatically SIwave assigns sink to the CPU and source to the VRM. Now, if I want to calculate the equivalent circuit, you have to select both of them. So you have to select 2 lines per power plane, then compute RLGC. And notice these are the values, and also notice the units used. So this is the resistance, this is the inductance, this is the conductance, and this is the capacitance in picofarad, of course. So that's how much you have it in picofarad. You can export RLGC subcircuit, and SIwave allows you to export it in using different format. Depends what kind of, where you're gonna use your file. You can enter the name. You can enter the number of lumps. So practically, you can have one set. You can have many of them. Like in this case, I have 4 of them. So sometimes you don't want them to be only one lump. Maybe you want them to be distributed over a group of them. Then we have the MCP. MCP stands for Model Connection Protocol. And what is this going to do if you select die, package, or PCB? Let me show you here. Practically, is this equivalent circuit? Is it for the die? Is it for the package? Or is it for the PCB? And all what it does, it will add these additional lines, MCP lines, that talks about whether it's a die file, or is it a package file, or is it a PCB file. Or you can select none. You can select none. Then it will not add these lines. Then you click OK, and it will produce a file for you that you can use with so many other kinds of circuits. one of the first thing you want to do when you finish solving a model is to check the mesh. Sometimes it's good to verify the mesh. As you know, because this is a PCB structure, SIwave uses exactly the same mesh in all layers. So it's the same 2D mesh. So you can zoom in on different sections and see how good or bad your mesh. So check the VS area. If you're not happy and you want more accuracy, you can increase the accuracy required. You can increase the tolerance required for the solver. So this is something good to check and to verify. You can also do verifying the profile, and simply the profile will give you more information about how much triangles have been used in each section. And you can use this when you do comparison with other models that you solved before, or the same model with some modifications, but the previous ones you were happy with the results, so you know how much accuracy or how much mesh should be there for you to trust the results. So you can keep record of this for future comparison. Now, what else can you do? You can also verify the simulation properties. So if you solve this problem long time ago and you forgot completely about the setup, simply you can select this option and you can review the setup that you did in order to produce this result. So that's something you can do at the beginning. You can also export your model to an IBIS file. So and ICM stands for Interconnect Modeling Specification. It is a behavioral ASCII-based file format at the end, and it's used mainly to represent passive interconnection. It is still an IBIS model, so the file does not contain the physical model of your power plant, but just a behavioral description of the circuit. You can also export to an Sentinel SSO netlist. So it's a file that's simply a netlist. Nothing doesn't have data. It's a netlist, and it's being used for also other applications. So it's available from SIwave. So SIwave will provide you with such file. Now, the last thing I wanted to show you is for export is the SPICE model. So this is the SPICE model. So you can select this one, and when you select the SPICE model, you can change the output format, and you have so many kinds. Some of them are same like we talked about before, Touchstone, but you have other models that you can use to export your file. And this is a SPICE model that you're going to be able to use in a SPICE program. Well, that's not all what SIwave can do for you. When you use the PI solver, you can also export your data to a network data explorer. So what is a data network explorer? It's something that is provided with SIwave. It's a tool that comes with SIwave. We will have a special video for it, which allows you to process the S parameters. And the beauty of it allows you to verify the causality of your results and the passivity of your results, and do lots of things. As I said, there will be a special video just to talk about this tool that comes with SIwave for free. You can also export the result to SUtility, which is another tool from Ansys that allows you also to do quite nice stuff with your data. Again, we will talk more about it in a special video. So these two tools, the NDE and the SUtility, they comes with SIwave, as I said, and you can use them to do some different kind of checking and verifications for your data to make sure that the data are reliable, you can trust them. So checking the solution, displaying the data in many forms, exporting data in many forms, and many kind of post-processing. These are the things that you will be able to do through SIwave PI analysis. Thank you.